Now we will analyze our first type of circuit, that is source free RL circuit. So we will first discuss source free RL circuit. Source free RL circuit means here we will take a resistor and inductor, but will not consider any independent source with that. But the inductor what we are considering is initially charged to certain current. Okay, so we will, let me draw that inductor and resistor, and the voltage across inductor is VL and current flowing through that one is IT, and this is resistor R. And one more assumption is that I of 0 at t equal to 0, it is carrying a current I naught. So this is the condition. Now we will find the response, we will find an expression for I of t in this problem. Okay, so let us write first the KVL and write the equation first. Later we will see how we can solve that. So if you apply KVL, so what is the first one? First one is I into R. This we will apply like this, I into R plus VL equal to 0. This is the KVL. Now we will substitute VL. What is VL? Voltage across inductor. How it is defined? It is nothing but L di by dt. Okay. Now you if you divide the whole equation by L, so I will write first di by dt plus R by L, and this is R by L what you are getting here, and into I equal to 0. So this is a first order linear differential equation. First order linear differential equation. The order of the differentiation is only 1, highest order is only 1, and constant coefficient it has. So it is nothing but a linear differential equation. Now from this equation we would like to find expression for IT, or in other words I can tell solution to this linear differential equation is nothing but our analysis of source free RL circuit. So we will get an expression for IT. That is how we come to know the response. Okay, so how we can solve this one? There are many how to solve this differential equation. There are many methods. Variable separation also you can use, but the easiest one and straightforward is we will assume a solution and we will substitute that into the equation, and then we will find the response. Okay, that is the easiest way. And while assuming also, if we assume an exponent, or I can tell like this, any signal can be represented by an exponent or sum of exponent. So in that way we can safely assume a solution with exponent terms, and it turns out that in many our electrical problems exponent or sum of exponent will be the solution to our problems. So we can safely assume, so we will assume the solution, assume I of t. We will have many coefficient here, many unknowns, so that we can substitute them. Okay, so I of t equal to a, we will add one coefficient a, and exponent e power s1 t. Anyhow, it is dependent on t. So t variable will be there, and we will assume we can safely assume an exponent, because any signal can be represented using an exponent or sum of exponent. That only you are studying in other subject also, many series and linear transform, there you are going to use exponent only. Okay. So let this be the solution. This is the solution we are assuming. Now we will substitute this one in this equation. I will call it as 1. So d by dt of I means here a into e power s1 t plus r by l, and I is again, that is a into e power s1 t equal to 0. Now if you differentiate this one, a is outside and s1 is also a constant, you take outside, then what you get is e power s1 t, and here it is r by l, a, and as it is e power s1 t equal to 0. Now how we can further solve? The common term we can take outside, that a into e power s1 t, remaining is s1 plus r by l equal to 0. So if you find a solution, if you find the solution for this expression, then we can easily find what is the response I of t. Okay. So now what is the solution for this? So solution for this is either a can be 0 or s1 can be a minus infinity. But in that case, what happens? Our assumed solution, if a equal to 0, s1 equal to minus infinity, then our response will be 0. So that when that is a trivial solution, we will not use that one. The probable solution will be this s1 plus r by l equal to 0. So this can be a solution, s1 plus r by l equal to 0, and s1 is nothing but minus r by l, minus r by l. This can be a solution for our differential equation. So we will substitute this one in the assumed solution. What is that assumed solution? We have assumed I of t equal to a into e power s1 of t. This is the assumed solution. In that s1 we have found. What is that? A into e power minus r by l t, that is I of t. Now only unknown is remaining is a, we have to find. That we can find using the initial condition. We know that it's already given in the definition. I of 0 is known, that is I naught. Can we use that one to find out the value for a? Let us try that. So I of 0 equal to I naught, we will substitute in this equation. I will call this as equation 2, and in this 2 I of 0 will substitute. So I of 0 equal to I naught, that is nothing but a into e power t equal to 0 you have to substitute. So e power 0. So then what will be a? E power 0 is 1. So a is nothing but I naught. So our assumed solution, what we assumed solution, that is I of t equal to a into e power s1 of t, that will be I naught and e power minus r by l t. So this will be the solution for our source free RL circuit. So what information it is giving? The current, we will go back to that circuit. In this, inductor is initially charged with a current, charged to a current of I naught. Now if you keep this circuit for longer period, what happens? Your I naught, the current through the inductor will have this form. What is that? I naught e power minus r by l t. That means it is exponentially, it will be decaying with the initial value I naught, and if you keep on increase t value, finally it will reach 0. So inductor current will have the form of exponential decay. So we can call, if you have R and L is charged to an initial current I naught. If you keep that circuit for a long period of time, the current slowly decays, that is exponentially decays, and exponential constant will be what? R by L, that is a decay constant, and initial value will be I naught. So this is the solution for a source free RL network. Okay, so and this equation S1, and we have this S1 plus R by L equal to 0, this is actually called a characteristic equation. This explains the behavior of the circuit, so we can call it as a characteristic of the circuit or characteristic equation. Okay, now we will see solve one problem, then you will understand clearly what it is. Okay, so we will take the first problem. So for the circuit shown below, find voltage V at t equal to 200 millisecond or 0.2 second. Okay, and circuit is given here. Let's see the circuit. This is a voltage source with value 24 volt, and here we have a switch, and switch direction is given like this at t equal to 0, and V is voltage across this is V, and this resistance value is 40, and this resistance value 10, and this is 5, and current through passing is IL. So what is this circuit? This circuit, there is a switch at t equal to 0, this switch will be opened. At t equal to 0, this switch will be opened. So what we will do now, before t equal to 0, what is the equivalent circuit diagram? After t equal to 0, what is the equivalent circuit diagram? That we will write first. So first we will write when for t less than 0. So that time, what is the circuit? You have a 1R circuit here, and this switch is closed that time. So we will write like this, and we have one more, and this is 24, this is 40, and this is 10, this is 5, and this is IL, and we have voltage V here. This is for t less than 0. When t is greater than 0, for t greater than 0, so what is the equivalent circuit? That time switch is open, so 24 volt will not come into picture. So our circuit diagram will be (10, 5, 40 V), and this is IL. These are the two equivalent circuit diagram. For the same circuit, we have two models here. One when t is less than 0, another one is t is greater than 0. This is the first step. Second step we have to do, we have discussed the initial condition of inductor in the beginning, so that we have to use. So that means for t less than 0, this is the circuit, and a constant DC current is flowing through this. When a constant DC current flows through an inductor, how you can model that? It can be modeled as a short circuit. So it is assumed that here time period starts from minus infinity. So t equal to 0, at that time switch is open. So switch was closed for a long period of time. So that is the assumption. Switch is closed for a long period of time and the circuit is already attained a steady state. So a DC current is flowing through the inductor, hence the voltage across inductor will be 0. So I can model like this. This inductor I can write it as a short circuit. So this is 10, this is IL, and 24 and 40, and this is V. Okay. So inductor can be replaced by short circuit. Now for this we can find what? The initial current, whatever current is flowing through this circuit. So I can write that now IL is, what is the IL? IL is nothing but the current flowing through in the 10 ohm resistor. Same thing will flow into the inductor. So what is the current flowing through the 10 ohm? That is 24 divided by 10, 2.4 ampere. 2.4 ampere. You can see here 24 voltage battery appears across 10 ohm. So 2.4 ampere you will get. So what is this current? I can write like this. This is I of IL 2.4 ampere. It is the current at before time t equal to 0, or I can write like this: 0 minus I of 0 minus equal to 2.4 ampere. Why 0 minus? Because I am writing the equivalent circuit diagram before t equal to 0. So 0 minus is instant of time just before t equal to 0. So this is the situation. 2.4 ampere current is flowing through that. After t equal to 0, what happens? You are opening the switch, then our circuit diagram will be changed. So that we will write again. So this we will keep it, it will be useful next. So next one, for t greater than or equal to 0, or t greater than or equal to 0, okay, that moment of time. Or I can first, better I will just write first t equal to 0. I will write two diagrams. So at t equal to 0 plus, at that moment of time what happens? So at that moment of time you have again resistor here. Now switch is open. It is at 0 plus, switch is open now. So switch is open means we have resistor here, and so inductor, how we can model the inductor? Before opening the switch, a 2.4 ampere current was flowing through the inductor. So initially we have discussed that if you consider an inductor which is carrying current of 2.4 ampere or some certain amount of current, if you change the condition of the circuit, current through the inductor will not change instantaneously, because current resists abrupt change in the, inductor resists abrupt change in the it. Okay, so that's why what is the meaning of that? Soon after switch is open, that is I equal to 0 plus, the current what you get is same as I of 0 minus, because current cannot change instantaneously. So that will be equal to 2.4 ampere. So though you have opened the switch, 2.4 ampere current tries to flow through the inductor. So how we can represent that? So that we have discussed. It can be, inductor can be replaced by a current source, constant current source I0, and in that I0 value is 2.4, this is 10, this is 40. This is at what time? At t equal to 0 plus, that instant of time. But if you keep it for longer time, then I0, it is not a constant DC current. Current will see that exponentially decays. We already know that if you are not applying any DC supply to an inductor, current exponentially decays. So this is at 0 plus only, and after that This is the circuit. What is that? This one. This is the circuit. Initially it will be 2.4, then you can replace again by an inductor itself where current is decaying. So this is the circuit next. Okay. Now we have to find, the question is we have to find voltage V at 0.2 second. For that we will first find what is IL at 0.2 second, then we can substitute here. Okay. So this is our circuit RL. I will rewrite this circuit here. Since 40 and 10 ohm are in series, I can add those two, that will be a 50 ohm, and our RL circuit. So final solution for our RL circuit, source free. Our source free RL circuit will be 40 plus 10, 50, and you have an inductor of 5, and this is I. So we will first find expression for I. So for that, this problem already we have solved in the, we have derived expression for this. What is that? Solution will be, we can directly use that. Solution will be A into e power S1 t, where S1 is minus R by L. So in this case minus R, what is the R here? Resistance is 50 and inductor is 5. So we will get minus 10, S1 equal to minus 10. And what is A? That also we have found. A is nothing but initial current I naught. So that also we know, that is I naught equal to I of 0 plus. Soon after switch is opened, that time what is the current? That also we have already calculated that is 2.4 ampere. So in this solution we can write the response will be I of t equal to 2.4 into e power minus 10 t. So this is the solution for this RL circuit. So what does it mean? The current through the inductor exponentially decays with the initial value 2.4. At time tends to infinity, it will be 0. Okay. Now, but the question asked here is, what is the voltage across, not 50 ohm, voltage across, you can see here, voltage across 40 ohm they have asked. So what is the voltage, this voltage and this IL relationship? We will write that. That is nothing but V equal to IL into 40, isn't it? It's whatever current flows through into 40 is nothing but a voltage. So we will write that one. So V of t is nothing but 40 into I of t. So that is 40 into 2.4 into e power minus 10 t. Now what we want? We want V equal to 0.2 second. So that will be 40 into 2.4 into e power minus 10 into t. T is 0.2. So minus 2. So minus 2. So if you substitute that, 40 into e power minus 2 is 0.324 you will get. Sorry, not 0.34. This together, if you multiply e power minus 2 into 2.4, if you multiply, you will get 0.324. That should be multiplied by 40. So you will get one more thing here. This V of t should be sign we should be very careful. What is that sign? Just see, sign convention. Current IL is flowing like this. This is the current I direction. Voltage we are measuring, this is plus and minus. So current is flowing like this. Voltage you are taking like it is from our passive sign convention. Always current should enter into the plus terminal, not from minus terminal. In this case, what is happening? Current is entering at minus terminal and it is leaving at plus terminal. So our passive sign convention tells current should enter from plus terminal and leave in the minus terminal. So this equation I have to correct it. It is not simply 40 into I of t, it will be minus 40 I of t, because the current direction and voltage direction, if we compare passive sign convention, current is leaving from positive terminal. It should enter into the what, positive terminal, but it is leaving. So here also minus I have to write, here also minus I have to write. So this, if you substitute, you will get minus 12.99 volt. So voltage across the 40 ohm resistor at 0.2 second will be minus 12.99 volt. Okay, so that is the solution for this.